this video, we'll be looking at nearest neighbor algorithms for vector search and vector similarity. We'll be using a hands-on demonstration along with conceptual discussion so you can get the theory as well as some practical experience. We're going to be using Milvus as our vector database to demonstrate these concepts, and we'll be using Python to connect to that Milvus instance. Now note that the Milvus instance is itself installed on Google Kubernetes Engine in Google Cloud. So if you want to see how to install this yourself, check out the video linked in the description where I'll show you how to set up your own instance and then follow along. Let's go ahead and connect to the instance on Kubernetes Engine. For simplicity, we'll do that with Cloud Shell. We need to authenticate with the cluster using a gcloud command, and then if we check the pods, we should be able to see our Milvus instance running. Next, we're going to do a port forward to our Milvus instance using the standard connection port, so we can use this Milvus instance from our terminal. In a new tab, let's make sure that we have pymilvus installed. With that successfully installed, let's go ahead and boot up a Python interpreter so we can interact with this instance and the vector embeddings. The first thing that we'll want to do is make sure that we can connect to this Milvus instance. Since we're doing port forwarding, the instance should be available on localhost on port 195.30. Now let's go ahead and create a collection. For that, we'll need some more imports and some data types. We'll need an ID column, which would be our primary field, and we'll use auto ID for this field to keep things as simple as possible. Then we'll have our actual vector. This would typically be a relatively long vector, hundreds or thousands of float values. So we'll demonstrate that, but simplify things a bit later. We've now created a collection that we can use to talk about our vector search. We'll have an XY axis representing different vectors, which could be, for example, machine learning embeddings. We're going to perform a similarity search, trying to find the nearest vectors. We're going to start with the standard metric, which is Euclidean distance, which looks at the straight line distance between the vectors. Let's insert into our collection a couple of vectors. We have 1, 1, and 1, -1. Now we'll slim down our vectors to be just 2 dimensions and try inserting values using the collections insert method. All right, now that we have the syntax right, we just need to insert into our 2D collection, and we're looking pretty good. Next up, we might want to create an index which can help us with the vector searching. What this does is it tries to partition our vector space and potentially quantize it or other things to improve the performance of our search. This way, when we have a vector, it may be able to quickly find the nearest vector instead of searching every single vector in the vector database. Ultimately, we want to balance efficiency with accuracy. So let's create some index parameters for what we're going to be doing here. We're going to use Euclidean distance. Let's refer to the Milvus documentation where we'll find that our Euclidean distance is labeled as L2. This kind of looks like the Pythagorean theorem, which is deliberate as it's just a multidimensional version of that. Note that we have a range of different options for index types. These index types are the ways that we can partition and quantize the vector space to improve the performance of nearest neighbor searches. For our simple example, we're going to go with a flat, which is the simplest brute force type approach. Since we're going with a relatively simple brute force index, we shouldn't need any parameters here. So let's go ahead and create our index. All right, we've got a successful status code, so now we can search for similar vectors. For our querying, we'll want some vectors that we can use. Let's test, for example, what the Euclidean distance would be if our vector has value 1, 0. We should expect it to be equidistant from our other two vectors, being 1 unit away from each using this Euclidean distance metric. For the search, we're going to specify the same metric as in the index, and then we'll get our results from a collection search method. But we actually need our two-dimensional vector, which we can load like this. It looks like we added the index to our first collection and not the second, so let's now create the index for the second collection and see if we can execute our search. Okay, now this looks promising. We've managed to successfully execute the search. As we anticipated, the results reveal the distance. These IDs represent our two vectors, so we have a kind of matching between these points and these points. That's spot on with our predictions. To show the vector in a more customized output, we just add the output field's argument and voila, our vectors appear. Let's see what will happen when we employ a vector of -1, 0. Thinking about this intuitively, we're betting on the distance to be the square root of 2 to the power of 2 plus 1 to the power of 2, which equals the square root of 5. Let's create a new query vector as -1, 0 and rerun our nearest neighbor search. Bingo! As we forecasted, we hit a distance of 5 from both our vectors. Side note, when Euclidean distance is your ruler, Milvus skips the final square root. It's clear we can't run through every index type in this tutorial, but let us awaken your curiosity to know that they can pack a punch in boosting performance. Though we've used a blunt weapon, the brute force algorithm, be aware that it works best for smaller datasets. As for larger ones, nimble quantization and partitioning-based methods or even fancy graph-based indexing methods are worth it. Next, let's set our eyes on a graphical representation of the similarity metrics. Ziliz has crafted this neat chart showing Euclidean distance as the straight line between the two vectors. The inner product is the projection of one vector on another, and cosine similarity is only related to the angle between vectors. If you're a newcomer in this vector universe, we recommend going steady with the Euclidean distance. For mini projects involving vector databases, kick off with the flat index type and scale up to more intricate index types as your vector database grows. Ziliz features an auto index, which lets you relax. They've got your back on deciding the fitting index. We're attaching a clean version of this Python code and the diagram file as links in the description of this video, so you can easily use or modify these for your own purposes. Thanks for watching, and please enjoy responsibly.